Okay, let's turn to page 65, please, and look at this relationship between momentum and force. Now, we haven't defined momentum yet, but if you look on your formula sheets, you should see that on the front page there is a little formula for momentum, and I think it's actually the letter P on your formula sheets, but it should be the Greek letter rho, which looks a lot like a P, is equal to mass times velocity. So the momentum is, this combination of mass and velocity. So an object can have a lot of momentum if it's got a lot of mass. If an object has not got very much mass, it's going to need to have a very, very high velocity, like a bullet, in order to have a lot of momentum. All right? So we've got that little formula on our formula sheets. We also know that force is equal to mass times acceleration. That's Newton's second law. We can think of acceleration as being the change in velocity over time. So if something is accelerating rapidly, then we have a very large change in velocity over a small amount of time. We can also have a very low acceleration if something is velocity is changing but over a longer period of time, or it's not changing its velocity very much. So if we put that in, and we know that we've also used this relationship, as part of Newton's second law questions when we're explaining how increasing the time can decrease the force. And that is because we see here that the change in time is the denominator on the right-hand side, and so as this gets bigger, then the force must get smaller, assuming that the object is not, has a constant mass, which is a reasonable assumption. So what we do here is we can, if we think that momentum is mass times velocity, then we've almost got something that looks like momentum here now. What we need to do is move the time over here. So F delta t is equal to mv minus u, which is the change in velocity, isn't it? So if v minus u is the change in velocity, then what this is, F delta t, is equal to the change in momentum. So to change momentum, we have to apply a force. The longer we apply that force for, the greater the change in momentum. Now hopefully that sort of makes sense, that we can, this is also known as impulse. There was a question a couple of years ago on the exam, and it asked students to talk about impulse, and it was left blank by probably 70% of the state because they didn't know what the word meant. So it's important for you to make a note that when you're revising for this, that you know what impulse means. So the longer you apply this force for, the greater the change in momentum. And if you think of, we sometimes use the word like impulsive. If someone's impulsive, then they do something really quickly. So you can see how it relates to time, perhaps, that a force applied for a short time will change momentum, but a force applied for a longer time will have a bigger change in momentum. We can also look at the relationships between what happens if I want to apply the same force to two different objects with different masses. How would that relate? Okay, so maybe have a chat amongst yourselves. We've got a truck, car, we want F the same for both. So what are we going to see as far as what delta T? How long would we need to apply a force for?